combination pi square B average AC into 10 raised to minus 3, we will call it output coefficient. So this thing we need to remember. With the help of this derivation of output equation for DC, let us move to the output equation for AC, that is for particularly for three-phase induction motor or synchronous generator or synchronous machine in general. If we know the total number of phases, machines can be of single phase, two phase, three phase. You know that the servo motors are generally they are of two phase, and heavy induction motors are generally of three phase. So irrespective of the number of phases, if we know the total number of phases, and let us denote that by m, small m. And if you know the total rating of the machine in kVA equal to number of phase multiplied by output voltage per phase multiplied by current per phase into 10 raised to minus 3. So for kilo it is 10 raised to minus 3, and VA is for voltage and current. So the total power becomes M into EPH into IPH into 10 raised to minus 3. Jaldi, the terminal voltage of each phases may be taken equal to the induced EMF per phase. So this induced EMF is also equal to the terminal voltage of the machine. So therefore the induced EMF equation is equal to 4.44 into frequency into flux multiplied by turn per phase multiplied by winding factor. This is a small difference of EMF equation compared to the DC machine. We never find this winding factor in DC machine because it is entirely a different pattern of winding that is used in DC machine, whereas in AC machine we use a star and delta winding. And this winding factor is introduced due to the distribution of the winding, and also sometimes short pitching of these windings are required to remove the harmonics. And the value for this kW winding factor for a balanced three-phase machine is generally it is equal to a constant 0.955. So if I substitute this EMF equation in the power equation, so the equation modifies to M into 4.44 into frequency multiplied by flux multiplied by turns per phase winding factor IPH. Simply substituting in place of frequency P ns upon 2, P number of poles, ns synchronous speed in RPS. So if I substitute this value in the main equation, then after a short manipulation we can get this equation 1.11. Instead of 4.44, simply by dividing this denominator 2 we will get 2.22, but we want another 2 to be multiplied with MIPH. So in this way we would need another 2 in the denominator, that will cancel out. So we will have twice times 2 in the denominator, it will make 4, and 4 in denominator and 4.44 in numerator. So we will have 1.11, this quantity multiplied by kW, P5 into 2 MIPH TPH into NS into 10 raised to minus 3. Now again, here our effort is to give it a form where I can find total magnetic loading and total electric loading in this equation. I can clearly see P5 in the bracket, which forms total magnetic loading, and I can use this P5 to replace it with specific loading and product of main dimension. But what about this 2 MIPH TPH? We know that for a circuit having one or maybe a machine having one circuit per phase will always have a conductor current Iz equal to phase current. So the total number of armature conductors Z for me is number of phases multiplied by 2 into turns per phase, 2 mTph. So this constitute capital Z for me, total number of conductors. So the equation now becomes simple. I can replace Iph by Iz and 2 mTph by Z. Now this equation got its proper form where I can replace the total magnetic loading and now total electric loading Iz into Z by their respective specific loadings. Now we are at the end of the derivation. By simply substituting these values in equation 4, I will have 1.11 into Kw pi dl B average pi d AC ns into 10 raised to minus 3. Now taking out all these constant 1.11 and their twice pi is coming, so pi square, B average we can take out, AC we can take out, Kw is also constant, and 10 raised to minus 3. And separating out the dimension part like d square L and finally the speed. Isn't this a derivation very similar to, now it is now looking similar to a DC? But there is a small difference, not in terms of d square Ln, because d square L is very, this quantity is common and this generally represents the volume of the machine also. So this is common between AC and DC output equations. But in place of speed, here the speed is synchronous speed, and in place of C naught, the quantity besides B average, AC, the quantity takes Kw also. And the numeric figure last time we saw was only pi square. Here it is pi square into 1.11, which comes out to be around 11, approximate 11. So there is a difference of C naught, output coefficient for the DC machine and AC machines are different. So the final equation Q equal to C naught d square L into Ns is output equation, where C naught is output coefficient. The equation 3 that we saw in the DC machine is, we know that it is termed as output coefficient, but we should not confuse the power PA developed by the armature with rated power of the machine. Also, distinction must be made between the generator and motor action. Consider a DC machine, shunt machine acting as a generator. The prime mover must supply friction, windage, iron losses which do not exist in the absence of rotation. The armature supplies its own copper loss and also the field copper loss. So the power developed by the armature for generator is equal to output power plus the power being supplied to the armature and lost as I square R, and also generator is providing power to the field winding. So the total power generated by a DC generator is output plus the armature losses plus field losses. So, and also it is also equal to, if you know the input power, where we will get this input power, it is nothing but the power provided by the prime mover minus the mechanical losses like friction, windage and iron losses. So in this way, if you know the input and if you know the output, so output upon input is efficiency. So input is output upon efficiency minus the friction windage iron loss. This is another form of equation to find the total armature power, because this is the armature power that would be used in the output equation. And from the similar analogy, the armature power for the motor is output power plus friction, windage and iron loss. For large machines, generally these friction windage losses can be neglected, and armature power for generator, it is equal to output power divided by efficiency, and for motor the output power can be considered equal to the armature power. But in small machines there is a considerable difference between the armature power and rated output, as the friction windage losses are relatively large and thus cannot be neglected. So this was the additional important note on output equation. Sometimes the output of a generator or motor in HP is also given. Like in motors, generally the output is given in horsepower. So you should be able to convert the horsepower by multiplying by 0.746 and then use that equation for output equation. Revise the topic from the reference text like A.K. Shawnee or M. Ramamurthy for his optimal design equations, constraints and variables. And for further query, you may contact me on this email ID kaushalnaik@gmail.com. Thank you.